So very good morning to all of you. In previous lecture, we have started the design of uh, gusseted base. So this example we have solved. I will go through it and we will complete this design and then see the moment resisting gas. So a column of ISHB 350 about 67.4 kg per meter carry a axial compression factor load of 1800 kN. Design a suitable bolted gusseted base. Rest on M20 grade of concrete. Use diameter of bolt 24 mm of grade 4.6 for making the connection. Okay. Step number 1, we have to write down the given data. It is already completed. Step number 2, we have to find out the bearing strength of the concrete which is supporting the base plate or gusseted base. Area required, you can find out in step number 3, which is coming 200 into 10 to 3 mm square. Now, selection of the gusseted material in step number 4. Gusset material consists of gusset plate angle. So already this we know that to draw a figure, so we have already drawn a figure, and this is the gusset plate and the gusset angle. Gusset plate and gusset angle. Okay. Now, in step number 4, we have to decide the gusset plate and gusset angle, that is gusset material. So we have decided that the gusset plate thickness should not be less than 16 mm. That's why we are gone through the thickness of gusset plate 16 mm. We have taken here thickness of gusset plate 16 mm. Okay. And the gusset angle and same approximately same thickness with the gusset plate. So we have chosen the ISA, 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 ISA 150 by 115 by 15 mm. Sorry, from the steel table or IS 808. The check is that the longer leg should be greater than 100 mm for the requirement of the connection, for the requirement of the connection. All the students requested to join on time. We are disturbing the class already 10 minutes over. Now we can find on step number 5 the length of plate. Length of plate is nothing but the depth of the column D plus 2 times of thickness of your gusset plate, because both sides you are providing with both flanges you are providing the gusset plate, and 2 into shorter leg of the angle which we are providing. Okay, plus overhang, plus overhang. Okay, so this will give you the length of your plate. This will give you the length of your plate. Okay, so you can calculate the length of plate. You can calculate the overhang provided to around of the plate. Then you can find out the breadth of plate, that is area divided by length of plate. So area divided by area divided by length of plate will give the breadth of plate, and that is coming to 22.58, as we will round up. That is breadth of plate is 330 mm, which is greater than the width of flange, which is greater than the width of flange. Okay, area provided you can calculate now, and that is length of plate into breadth of plate. It is coming 204.6 into 23 mm square. Okay, in step number 6, you can find out the intensity of upward pressure due to the concrete foundation, and that is nothing but load upon your factor load upon area provided, that will give you the upward pressure intensity due to concrete, and that is the calculated 8.8 Newton per millimeter. Now in step number 7, you have to calculate from the section, you have to find out the value of the C, and you have to find out the maximum moment. Okay, from the critical section. The critical section lies at the toe of your angle section. The toe of your angle section. So this is your angle section at the toe of the no, at the root of the angle section. Sorry, at the root of the angle section, and then you have to find out the value. It is the overhang value, that is C at this. So you can find out from this portion. From this portion, you can find out the bending moment, or this portion you can find. Both will be the same. So if you find out the critical section load, the moment, the maximum moment, you can calculate it, and how you can find out the value C, that is the cantilever part of your base plate. So 620 is the length of your plate, the depth of column D minus 2 times of thickness of the set plate minus 2 times of thickness of your angle. It will give the value C divided by 2. Okay, so we calculated the C is coming around 104 mm. Then based on the value C, you can find out the maximum bending moment of the cantilever portion if you calculate. So this is the CG of your rectangular section. That is CG is at C by 2. Okay, and uniformly distributed load is there. So hence the total load is W into C. That is capital W. Capital W is nothing but W into C into the distance from the critical section. It is C by 2. The maximum bending moment will be WC square by 2. Okay. Put the value, you will get the maximum bending moment, that is 47.59 to 10 raised to 3 Newton mm. Okay. Now we know the design strength of your section. MDG is equal to 1.2 times of ZE FYG gamma M0. ZE is nothing but the elastic section modulus. ZE is nothing but the elastic section modulus. Okay, so you can write down ZE is equal to I upon Y bar. Okay, so I upon Y bar, you can know the I is BT cubed by 12. Okay, and Y bar is T by 2. If you equate this, the T square by 6 will be the ZE value, because you are considering the unit width of your foundation. So B is equal to 1. The unit width we are considering, that's why B is equal to 1. Put the value, the MDG will be 1.2 times of T square by 6 into Fy is 250. Now we can equating moment with the moment of resistance. Equating moment with moment of resistance. Moment of resistance, that is MR. So we know that MDG is half into T square by 6 into 50. If I will write down T square, so all this 250 into 1.2, it will come another side, 6 will come up another side, into 47.59 into the 3 the moment. Okay, under root of 28554 were 300. So when we find out the number 2, we will get the value of total thickness of your base plate. So total thickness of base plate already you have provided the angle thickness of 15 mm. So this is TA is nothing but thickness of your angle. Thickness of angle. So already angle section we are providing with the thickness. How much? How much thickness? We are providing the thickness of 15 mm. 15 mm. So 30.85 minus 15 is the, so it is coming 16. 15.85. If you round up, the thickness of base plate will be TB, and that is 16 mm. Hence, provide thickness of base plate 16 mm. So up to this, your uh, design is completed. Then we have already find out uh, uh, the value of, yeah, decided the uh, we already decided the size of base plate. Okay, the size of base plate we got, it is around uh, 620 by the length of plate into breadth of plate into thickness of plate. Okay, so if you write down this, length of plate is 620, we have decided. Breadth of plate we have decided 330 mm. Okay, and thickness of plate we got 16 mm. Okay, so this is sizing of the base plate. So we have calculated the size of the base plate. Okay, now we know that. So if I will draw the figure, then you can draw like this. Over, this is the column going through, and so please understand. This is the column. Up till now, we have decided the, this is column, the thickness of plate. This is the thickness of plate PG. So taken 16 mm. Then unequal angle section. We are quadring at both sides, and this is thickness of this angle is TA, and TA is 15 mm, and depth of your column is 350 mm. So this thickness of this gusset plate is uh, connected with the column. So you can draw this the uh, bolted connection, because it is bolted connection. Then gusset material, that is gusset angle, also connected with the column through the gusset plate, and then this shorter leg is connected with the base plate. And also the thickness of base plate we have calculated. This is thickness of base plate. We have calculated base plate. We have calculated is how much? 16 mm. And this is the length of plate. That is also we have decided is the length of plate, and it is 620 mm. Okay, and breadth of plate we have calculated 330 mm. You can draw like this figure. Okay, draw properly, because I'm going there is a problem. That's why it's not straight lines. Okay, so this already up to this we have done the design. Okay, now step number 7, you have to uh, design the bolted connection. Because the bolted connection is given, so step number 7 is design 7 or 8, whatever it may be, you can write down. Okay, design of bolted connection, because bolted connection is given, and size of bolt D is given 24 mm. Okay, so you know that the design strength of bolt is minimum of VDSB and VDB. So you know that the bolt value or design strength of bolt is equal is minimum of shearing strength of bolt and bearing VD bearing strength of bolt. Okay, so you have to find out the bolt value or shearing strength of bolt, bearing strength of bolt. You know that in example, these values are given. Okay, these values are given in the example. If you see, so the values are given in the example. Grade of bolt, grade of concrete, grade of bolt. Okay, also thickness of flange, width of column, thickness of web, thickness of flange, all these values, radius at roof, radius at toe, all these values are you can take from the steel table and is given. Okay, and diameter of bolt is also given 24 mm. Diameter of bolt is also given 24 mm. So we know that the diameter of bolt is 24 mm, then D0 is equal to, you can take 24 plus 2, or you can go for the IS code. In IS code, the section number 10 is nothing but design of your connections. If you come to the section number 10, so here the clauses are given, and on table number 20, table number 19, I think so. This is table number 19, where it is given the clearance for the fastener hole. If the diameter of bolt is 24, then the standard clearance will be 2 mm, and oversized clearance in diameter is 6 mm. Okay, so we'll consider 2 mm. So what it will be to write down here. So diameter of hole we required, diameter of hole plus clearance of 2 mm, which is coming 26 mm. It is coming 26 mm. Okay, so this clearance we have taken from table 19 of IS 800, page number 73. Okay, so you know the diameter of bolt, you know the FYB is 240 Newton per mm square, FUB is uh, 400 Newton per mm square because of black bolt of grade 4.6, and how to calculate just now I have told you that if the grade of bolt is given 4.6, the first term you take to find out the FUB, and that is first term multiplied by 100 will give the ultimate strength of your bolt material, and that is 400 Newton per mm square. Similarly, you can find the yield stress of the bolt material, that is FYB. This value, you calculated the ultimate value into the value after the point, that is 0.6. It will give the yield strength of your steel. Okay, so likewise you can find out. Now, the bearing strength of bolt or shearing strength of bolt is VDSB, that is shearing strength of bolt. It is shearing strength of bolt, and the formula is given. VDSB is equal to VDSB is equal to 400 under root of, sorry, I will write down formula first, so it will be uh, remember to you. FUB upon root 3 into gamma M0, gamma MO, okay, or gamma M1, because here ultimate load is there, so you can write down gamma M1. Or if it is a bold material, you can write down gamma MB. Clear or not? Okay? Into NN ANB plus NS ASB. Because this value will be zero, because 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 bold is bold is common bold. Common bold means that it is fully threaded. If there is no sample area, if the board is fully threaded, then the NS value will be zero. If that whole term will be zero. But I will write on FUB is 400 root 3 into gamma MB is 1.25 and NN is equal to NN is equal to, I will take one number of shear plane, I will take 1 and B is the point A, 28% of area of that whole 5 by 4 into 24 square. Okay, so we'll get the VDSB value. VDSB value after solving this is coming 65.19 kilonewton. Now you have to find the VDPB. VDPB is also given in your VDPB is also given in your clause in IS code on page number 2021. So VDPB is 2.5 times of KB into B into T into FU by gamma MB. तो KB की वैल्यू आपको मालूम करना है KB is equal to E upon 3D0 E upon 3D0 E upon 3D0 minus 0.25 minus 0.25. Okay, FUB upon FU and 1. So KB value is minimum of above 4 values. इसमें जो कम है वो आपका KB है. So if I will find out E upon 30, so E is equal to 1.7 times of 30, then put down 1.7 into 26, 0.7 into 26. For hand flanker, it is coming 44.2 mm. Okay, and P is equal to 2.5 times of D. 2.5 times of D is 24. 24, 2.5 into 24, it is coming 60 mm. It's coming 60 mm. So now put the value, you can find out P upon 3D0. P upon 3D0 is equal to how much? 0.56. P upon 3D0 minus 0.25 is 0.52 and third value is 0.17 and fourth value is 1. So this value is minimum of that. Which one? This one is the minimum. Okay. So it means that you can put the value in the KB is equal to KB is equal to 0.52. It means that the KB is equal to 0.52. Now put the value that VDPE is equal to 2.5 into KB is 0.52 into D is 24 into T is 24 into T is the thickness of flange you can take here, because thickness of plate is 16 mm and thickness of flange is 11.2 mm or 11.6 mm, I think so. So in this your lecture it is already given. The thickness of flange is 11.6. I will write here 11.6. Okay, are you getting? समझ में आ रहा है आप लोगों को? समझ में आ रहा है क्या भाई लोग? Okay. So this is up to the design of connection. So 2.4 we are finding on the bearing strength of the board. So 24 into 11.6 thickness of flange into Fu is 410 divided by gamma MB is 1.25. Putting all this value and calculating, it is coming 118.7 kilonewton. Okay, it is much larger than the DSS. So what is the bolt value? Bolt value is minimum of bolt value is minimum of VDSB and VDPB. Where VDSB is the minimum, so bolt value you can write down. Bolt value you can write down. It is equal to 65.2 kilonewton. Okay. Now easily you can understand and find out the number of bolt required. The number of bolt required is equal to number of bolt required is equal to required two flanges are there. On one side, it is equal to load is 1800 divided by 2 divided by 65.4 is coming around 13.846 13.846 volt are required. Let us provide let us provide let us provide 16 number of bolt of size 24 mm. That is also black bolt. Okay. So this is nothing but the connection design between the gusset material and the angle. So how many bolts required at one side? 16 number of bolts. So how you can provide the bolt? You know, now you have to draw the sectional elevation with another direction. This is your flag is showing. I will break the line. This wave at the center. Okay. पहले वेव आपका सामने नहीं दिखता था, लेकिन ये साइड से आप जब देखेंगे आपका वेव कहाँ रहेगा? सेंटर में रहेगा. Okay. Now you can draw this with the plane, front of the plane, In the draw this the plate we are providing attached with the column, then the angle you are providing, this is the angle, and something else, okay, and this is the dotted line of the edge of your column, okay, you can provide, आप क्या provide करना है आपको, number of bolt आपने जो मालूम किया, so you know that 16 bolts are there, so this dotted line here is flanges, you cannot provide the bolt at the plane position, okay, so provide a bolt here, one number of 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 bolt here. So 8 bolt connected with the column and 8 bolt connected with the angle to the base plate. So this is nothing but your design, and you can write down the design summary. The thickness of the base plate is also 16 mm. Okay, this is the longer leg. Right, this is the longer leg, 150 mm. Okay, and this is nothing but S0, that is S0, that is slope. Okay, and then we will provide the angle to accommodate within the dimension. So how many bolt I provided? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, 14. So and then bolts are provided and 24. You can find out the edge distance, end distance. Okay, the distance you measure in the direction of course, that is the end distance. If you are measuring distance from the edge of the board to the center of the board, with the direction of your uh, force, and that is called as gauge distance. Now you can write down the design summary. Here the width of flange is 250, okay, and meeting the breadth of plate in this direction you will calculate that is 335. Likewise, you have to provide or draw a figure and write down the design summary. The size of plate, you can write down design summary. Design summary, you can see here, you write down the design summary. So first is the size of gusset plate, gusset plate, size of the gusset plate. So write down is 620 by 350 by the size of the circulate. So 150, and then the plate we will take the distance. Okay, so this is the head distance. Okay, this is the end distance, and in between the P. If I will decide, so P is already we have calculated this coming end distance or end distance. This how much distance calculated earlier. डिग्री तो एक 44 पॉइंट अगर 50 एम पर हम पकड़ते हैं तो एन डिस्टेंस इज 50 एम 50 into 2 will be 100 mm plus pitch is 2.5 times of 2.5 times of 3 is 24, so I will multiply this 2.4 0.5 times of 24 is 60 mm. The pitch is coming 60 mm. 100 plus 60 mm is 160 mm. Okay, we'll write up, make a greater 200 mm plate. The length of plate will be 350. The size of plate will be 620 by 350 by 60 mm. Size of gusset plate. Second, size of gusset angle we have decided successfully is 150 by 115 by 15 mm. On the dimension and writing in mm, okay? Design symbol. Third is the base plate. This all are the design. Design means deciding the dimensions of the sections, size of base plate. I will write down the calculated 620 by 330 by how much? It is 16. So this is nothing but your design of your gusseted base. This is nothing but your design of the gusseted base. Okay, so that we can and there are some check are there. Check is that S0, this distance S0 S0 should be less than or equal to 13.6 epsilon into Tg. Tg is the thickness of plate. This is S0. Okay, so you can find out this. Okay, this value, and you can check, you can calculate this from the geometry and calculate this. This Tg should be less than the Tg required. Then it is okay. Then it is okay. Okay. Also, the thickness of flange is less than the thickness of gusset material or thickness of base plate, provided that is 16 mm and thickness of flange is 11.6 mm. So we are our design is complete here, and these checks are given in the score. So, okay. So likewise, we complete all the design calculation for the gusset plate design. Okay, if you have any question, you can ask with me. Otherwise, we proceed. Now we see the moment resistance base. See the moment resistance base on moment resistance base. This is already uh, notes of name, file name is SD underscore 01 203 S3. This PDF file I will share to you, and that there is given. You will see that also the design of moment resisting base plate. Why this is moment resisting base plate is required? If there is eccentricity on the loading and there is moment on your base plate causing ununiform compression due to the moment, okay, so that's why at that time you need the moment resisting base plate. So moment resisting base plate, you can see that there is one side the compression is greater and other side is less. It is not uniform. In case of axially loaded column, this is uniform. But in case of this, uh, your uh, moment with the axial, the, you can see here the stress distribution of axial load P by LB. So this is the stress diagram you can see. Okay. So stress is nothing but load upon area. Load is P and L into D is nothing but area. So this is uniform throughout. But if bending stress is there in distribution, so one side you can feel a tension and one side you can feel a compression. So it is one side 6 PE by BL square and another side 6 PE upon BL square. So that is the bending stress distribution if there is movement on the column. You combine the distribution, this axial load and bending stress distribution, if you combine, you can say that combined axial load and bending stresses, so it will be PL 1 minus 6E upon L or PLB 1 plus 6E upon L. Okay? And if there is tension, and if combined stress for no tension, if there is no tension, then at one side there is 0 and then that 2P upon LB will be the maximum stress at another side. So this is the stress distribution for the your moment resisting gas. Okay, so that you can calculate it. There is three cases you can go. So if you see the base plate A, B, C, D, okay. So A, O, D, okay. So at O, at here is the stress is zero, and if I proceed that negative stress is there, then it can be the tension at this portion. At this portion, okay, there may be tension, and here stress is zero. Okay. So stress distribution for small tension, figure 3. You can see here also and here also. Okay. Okay. So if I write down, let the column is subjected to a load P at an eccentricity of E, causing a moment M is equal to P into A. Because load into distance is nothing but the moment, and an axial load P. This gives rise a combination of axial compressive stress and bending stress. Because there is moment, that's why the compressive stress and bending moment both are there. We can say that that is combined axial load and bending on the column. Due to axial load, the pressure distribution is uniform and stress diagram is rectangular, as shown in the figure A. See here the stress diagram is uniform and it is rectangular. Okay. And the stress diagram is rectangle shown in figure A. The direct stress P upon AR, P upon LB in case of axial. But due to bending moment, the bending stress develops plus minus M upon I into Y. So this bending moment will be developed. Okay. So you can put this value for the rectangular selection plus minus M upon BL cube by 6 into L by 2. This will be BL cube by 12, that is I. This will be cancelled, so 6 will come out. 6 MBL square. M is nothing but P into V. M is nothing but the moment, and moment is nothing but P into E. P is the eccentricity, P is the load. So it is nothing but if you write down the intensity of pressure is different at different place. So you can write down this with the bending it is 6 PE BL square. So 6 PE PE divided by BL square. If you will take the longer side, another side you see, then it is LB square. Okay. So combined effect, if you can write down, so this will be plus minus the combined stress to the axial load and bending moment as shown figure number 3. So it may be plus or minus 6P or 6N by D square. This is nothing but N. Okay. If I will take the P common, LB common, so it will be ELB common, so 1 plus minus 6 E upon L. This will be the final. In case of axial load with bending moment, the stress you can find out P upon L be 1 plus minus 6 E upon L. 6 E is the eccentricity, L is the length of your base. It is desirable to have a combined stress compressive stress throughout, otherwise contact with the concrete block is reduced due to the tension, which increases the stress failure. Depending upon the eccentricity, m is equal to, or you can write down E is equal to m upon P and length of the base plate. So therefore, there are three cases possible when there is no tension. So if there is no tension, then E is equal to L by 6. E is equal to L by 6. And when tension develop is small, then E will be in between L by 6 and L by 3. And when the tension develop is suitable or substantial or large, can say that E is greater than L by 3. So this is all about the theory about the moment of resisting base. So that is all about the unit number 3 part B. So today our unit number 3 is also completed. Okay. So again I will share this notes on the Google Classroom. You can go through it and design the example. Okay. I will share the assignment also. We'll stop here. If you have any doubt, you can ask with me. Otherwise, आपको कोई डाउट है कुछ पूछना है तो आप पूछ सकते हैं. Otherwise, हम stop करते हैं. Ahmed, Arif, any question? Will you stop?